Okay, we will come to the first to the slides. Okay, today we'll talk about the angular momentum of a particle, and there will be, of course, the angular momentum of a rigid body. In general, it's only matter of the geometry will change as the particle is only mass point, and the rigid body, there is in this case there is the behavior of the body, not the particle. Okay, now what we have seen until now, we have seen the impulse, which is defined, has been defined by this, the integral of the forces, which is equal to B, and B, the impulse, it's only the mass multiplied by the vector velocity. Okay, now we take the motion of a particle m in the plane. That it means we have our mass here m, it's applied on it the force F, and has also, let's say, moves in on the plane with certain velocity here v. Okay, now if we take an arbitrary point here a, okay, what we have here, we have the direction of the force F, we have the direction of the velocity v, and of course, if we look to the impulse b, which is only the mass multiplied by the velocity, it's clear that as the mass is constant, let's say, it's scalar, it's not vector. In this case, b will be in the same direction as the velocity. Here, if we look now to this coordinate system x, y, we have, of course, the let's say the axis z. Okay, now what we can define here, the angular momentum here of this particle m about the point OA. This is, we note it by LA. Okay, and this is will be equal only to L, the distance, multiplied by the impulse. That now it means that we take here the impulse, the direction perpendicular to it, let's say, as we do it for the moment. You have seen in when we describe the moment is only the force, multiplied by the arm, and the arm is perpendicular to this force, and we can take the moment about any point, that it's only the force multiplied by the moment, or we let it in vector. This will be the force cross product or vector product of the position or the distance, vector distance. Now this is L, okay, multiplied by this B, okay, which is the impulse. This is in general what is known. Now if we take it in vectorial, this is in scalar, in vectorial representation of the angular momentum, LA will be defined, okay, by the vector position R cross product, yeah, the impulse P. Now, as I said, here F cross R, okay, that means we have F here cross the vector position R to the point, the position of the mass M to the point A. This is the vector position R. When we do F cross R, this is will give the moment M A. Yeah, as I said, as you have seen it, yeah, in mechanics 1. Okay, now positive z direction of the angular momentum. What we do now, L, it's only R, yeah, sine the vector alpha here. Now, if we make R cross V, okay, we will be here R V sine alpha. Now, if we take this R sine alpha, it's only L, then will be L multiplied by the velocity V. Now there is what we call the change in the angular momentum due to the acting forces. Okay, the change means that, yeah, the during the motion, yeah, we look to the each change during the motion. That is means we have represented by the time derivative of the angular momentum. Okay, now we have this expression in vectorial representation. Yeah, in general case, let's say this is only the scalar representation. Okay, if we take this one, then if we make dLA, yeah, divided by dt, this is the change L dot, then will be here, as you can see, okay, there is two terms, yeah, and it means we have to make dr divided by dt, yeah, cross mv plus r cross dmv divided by dt, okay, and in mv here we have to make also dm divided by dt plus dv, yeah, multiplied by dt multiplied by the mass. Now, if we look in details, what we have here, LA, as I said, we have R, okay, cross M V dot, yeah. This is the derivative, yeah, where we make R cross D over dt of mv and plus this time derivative of dr divided by dt cross mv. Okay, as the mass, yeah, is constant, then it means the term when we make here r cross dm over dt multiplied by v, yeah, this is will be equal to 0. Yeah, as we know also that the vector position, the time derivative of the vector position, yeah, it's only the velocity. Yeah, this is, we have seen it, yeah, in, let's say, the part 1. Now, if we look here, if we replace now what we have here, we get R, yeah, cross M V dot. That is means only the first term. Why? If we replace now V by its expression here of R dot, what we get? We get V cross MV. Okay, M is constant. V cross V will be equal to 0 as they are parallel. Okay, if they are parallel, that is means um, the vectorial product or cross product, yeah, will be equal to 0. Then it means here, if we look, LA, the change in the angular momentum, will be defined by R cross MV dot, and the V dot, it's only the acceleration. Okay, as you know, A, it's only dV over dt. Yeah, from the second Newton law, yeah, for the force acting on the mass m, we know that F is only the mass multiplied by the acceleration. The force, the vector force, it's only the mass multiplied by the acceleration. Then we can make F here. We replace it here. Then the principle of angular momentum can be defined now by the change of the angular momentum. It's only the vector moment about the point E. Okay, this is keep it in mind, yeah, for the tutorial. We will use, yeah, this expression here, yeah. Now, if I summarize, we say the resultant moment, okay, this one, M, about point E of all forces acting on the particle M is equal to the time rate of change of the particle angular moment about point E. This is the general case. Now we take the principle of angular momentum for plane motion and circular motion. Okay, then it means that here for the circular uh, motion in the plane, we use in general, yeah, the polar coordinate system represented by the vector, unit vector AR and EV. We have now this angle phi, okay? If we take now our particle m, as I said, has the velocity v, okay? Now if we look to this mass here, this velocity here can be decomposed now into two vectors, which are the velocity v, the vector velocity v is projected along a radial direction and circumferential direction, which is represented by the unit vector F here. The same principle we use for the force F. Okay, if you remember now, we have here the velocity v and we have the force F, okay, acting on the mass m. Now the same principle F has two components, let's say, or two representation, F radial and F circumferential. Now in polar coordinate system, we know that the velocity v, yeah, we have seen this in kinematic in part 1, Vr, which is the radial velocity along AR plus Vp Ep. Okay, the same for the acceleration. Has one component in a radial direction and the second vector component, let's say, in um, circumferential direction. Okay, now what we do, the vector of angular momentum, LE, yeah, if we take the representation, it's only R, a scalar in AR direction, plus cross M, okay, and here M, we said is the velocity vector. The velocity vector now is decomposed into two terms or two components, which are radial one and the circumferential one. Now, if we take RER cross N VR ER, okay, the VR and R here are scalar, M is scalar. The two, let's say, components which are vector, it's only ER here. Then we have ER cross ER. This will be equal to 0, as is the same vector. And we know the cross product of parallel vector, it's always equal to 0. Okay? Now, we take the second term, which is R cross RER cross M V phi Fe. Okay. Now what we have, R a scalar, M a scalar, V phi a scalar. Now we have R M multiplied by M multiplied by V phi. This is what we have here. Okay. And we have ER cross Fe. If we look now to ER cross Fe, will give the vector which is perpendicular to the plane ER Fe. And the vector which is perpendicular to ER Fe as the unit vector will be HZ. Okay? Then this is the cross product of ER cross Fe will be only HZ here. Now, if we take the magnitude of angular momentum, LE, let's say a scalar, here will be R and V phi. Okay? Why? Because here this is the scalar terms, yeah, R and V phi, scalar term, and it said if we take now the magnitude of HZ, it's only the unit vector, but it means it's equal to 1. Then in this case here, we can represent R and V phi, yeah, and V phi, as we have seen it, yeah, it's only R phi dot. Okay, then it means we will get now it's M R square phi dot. Now, if we take the time derivative of angular momentum, this is what we call it, yeah, the change. This is, we call it the change of angular momentum or the principle of angular momentum. Now, if we take this time derivative, that is means we have to make the time derivation of this term here. Now, what we have R, ER, that is means here, cross M, the acceleration ER as we make the time derivative of M V dot here, yeah, that it will be here M V dot. Then we have here V dot will be only the acceleration. Then we have here M ER, the acceleration in radial direction along radial direction here, and the acceleration in circumferential direction, and this is represented by Phi. Now, if we make the time derivative of these terms here, okay, as we said, for the velocity here, RER cross MER, ER here, ER cross ER here, it will be 0, okay? Then we have only the term of RER cross EPhi, EPhi. And this is, as we said, ER cross EPhi will be only HZ. Then we get here the magnitude of time derivative of angular momentum, L dot A, okay, will be only R M Phi. And Phi, I repeat it, we have seen it in part 1, it's only R phi dot dot plus 2 times R dot phi dot. Okay. Then we have the Newton second law in phi direction. Then we have F phi, and F phi is given by this component here along phi direction. Then we have here MA phi, and Phi is given by this expression here. Then we have here the force component in circular direction with a moment about E. Then we can get that here MA, it's only R F circumferential in circumferential direction. Yeah. And this is will be R M Phi, as M Phi, it's only the force F in phi direction. Now, if we take this here for the principle of angular momentum, the principle will be only L dot, and L dot A is only the moment about the point A. Okay, then we can get here directly the moment about the point A. It's only L dot, and we replace the value that we obtained here by the following Rm R phi dot plus 2 times R dot phi dot. Now we say the moments are always positive if are acting in positive phi direction. Now we take here the example of circular motion. Okay, circular motion, that is means there is motion about the center A of the circle. Yeah. Then we have V L phi dot. This is the expression of the velocity. The example of the principle of angular momentum will be LA, which is LMV, okay, and V it's L phi dot. Then we have here ML square phi dot. LA will be here, if we look to this term here, ML square. This is, we call it by the moment of inertia of M about A, and this is only geometrical. Okay, that we have here EA, it's only the mass multiplied by the length square. Then for the principle of angular momentum, this is can be described by here for the moment MA, will be only equal to moment of inertia about the point A, multiplied by the angular acceleration, which is here phi dot dot. This is valid only here for the circular motion. Okay. we take the case of pendulum. This example, we will see it in the afternoon, okay? Um, where we have here, we have seen this example in the also in the previous lecture. We will see it, in the afternoon with the third exercises. And yeah, we will see for this exercises in the third exercise where we applied, here the Newton or the number method. There is always, this for this case we will see here the application of this principle of momentum. Now, if we take this case, what we have here, we have the mass m, and we have here the rod, let's say O and m, let's say this rod here. What we have? We have the weight of the mass point of the particle, mg, yeah, and this is it's fixed, yeah, at this fixed point here, and which can have along with the rotation about the point O or zero. And here we see the reaction, okay, of this hinge here. What we have? We have a R and here circumferential one, which I note it by ET, or you can note it also by E phi. Now that we have the length of this rod here, OM, which is the length here, L, okay, and here the pendulum, okay, will moves, according to this angle phi. Now what we have? We have the component of the velocity, okay, along ET or phi direction, circumferential one. This is, it's only L phi dot, okay? You know that it's only R cross omega. This is in general case, yeah? There is the component in radial direction, but if you have this component in radial direction, yeah, will cut the point. O is in the same direction as the rod, okay? This is will have no influence on, let's say, the change of momentum. Yeah, why? It's parallel to ER. Yeah. Now the support point or the fixed point here, O, point for the principle of angular momentum. That's what we have here by definition. This is the inertia. We take the inertia here, moment of inertia. In our case, it's I, A. In our case, it's I, O, yeah, phi dot dot. Then we have IO phi dot dot. This is will be equal to the moment about the point O. Okay, it should be the same point here. There is here a rod force, no moment about O. As I said, if you have the force here, if you cut here, okay, there will be the force in the same direction as the rod, and this force here make no moment about this point O here. Okay. Now, if we take the moment of the weight about O, that is means we have here M, G, yeah. We have the arm here perpendicular, and the arm distance here, it's only L sine phi. Then we have here the moment MO, will be only mgl sine phi. Now, if we take the principle of angular moment here, we have this term E0 is only ml, okay? And here we have here ml square phi dot equal to minus mgl sine phi. Okay, why? When we take here this term z, yeah, it's outward um, to the plane ER, ET, okay, and this moment will be in opposite direction as z. For this, we take here the sign minus. Now, if we develop, we simplify here. We cancel the mass m, okay, for length left and the right hand side. Then we will get here this equation phi dot dot plus g divided by L sine phi is equal to 0. This is what we have found, yeah, by using either D'Alembert or Newton law. That it means this is the differential equation. And if you remember well, we said, yeah, um, uh, the solution is always divided given by phi, which is here a sine phi plus b cosine phi. Okay, we make the derivation two times. We have to determine the constant a and b. Yeah, and this is you can see, yeah, the previous the same example, yeah, by using D'Alembert and Newton law. Now we take this example, which is the right moment of rotating a rod. Okay, we have this rod here, and it's rotating along this direction here like this. Then we have here the same principle. We have ER, the radial one, unit vector, EPhi, the circumferential vector, and we have the angle phi here. Okay, the mass has the velocity r phi dot. Okay, now we look to the moment about the point O. Then we have, yeah, here E0. It's multiplied by phi dot dot, which is equal to m0. Okay, this is the principle of angular moment. Now, if we make what we call the free body diagram of M, yeah, we get the forces. That is means here, we cut here, we make the free body diagram. That is means we cut here. If we cut, we have the force on the rod, and this force has two components, okay? The radial one and the circumferential one, okay? Ft, I noted by Ft, which is the tangential one. We can note it also by F phi. Yeah, it's a matter of notation, but the principle, or let's say um, the idea behind it always will be, yeah, keep it constant. Yeah. Now, if we look as they are connecting, if we make the free body diagram here, if we make the free body diagram, then it means the forces here are opposite to the mass m here, as there is equilibrium. Then it means the same forces here, Ft is opposite to Ft on the mass m, and Fr is opposite to Fr on the mass m here. Then it means here the two forces Ft and Fr, yeah, we take them here, and we have to make now only to determine the moment. The radial force of R, make no moment about the point O. As I said, Fr is parallel to the um, road, and there is no arm, okay, because the moment is always Fr multiplied by the arm, and the arm here is 0, okay. Now there is only the moment due to the tangential or circumferential one, and this is Ft multiplied by the distance L here. This is the R, okay? Now we have here the moment of the tangential force Ft by the point O in positive phi direction. It will be only Ft multiplied by L. Yeah, we apply now the principle of angular momentum. This is will be E0 multiplied by phi dot dot equal to the moment about the point O. This is the equation. Now we have mass less rod, okay, has no mass. Then we can write here the moment, yeah, it's only Ft multiplied by L, okay. And then we can determine the force Ft here, which is the moment about the point O divided by the length L. And with the principle of angular momentum here, we can determine now phi dot dot. Okay. Now we say, as we have done for the conservation of the impulse, here we say the conservation of angular momentum means no moment about fixed point O. Okay. Then in this case, there is ME will be equal to 0, as this terms is equal to this one, ME, that is mean the change of the momentum here will be equal to 0. Then we say here, if we integrate, okay, we will get here LE, it's constant. Okay. Now, if you return back to the central motion, the principle of conservation of angular momentum is valid in this case. Here, there is only the force between the planets. Then Fe here is equal to 0. Ma will be only R Fe, and this is equal to 0. Then it means here the conservation of angular momentum will be here Le, it's M multiplied by the position R between two planets, let's say, equal to mr square phi dot, and this is will be constant here. Then it means here phi dot, yeah, it's inversely proportional to the square of the distance between the two planets. And this is, we have seen it also, it's only the Kepler second law. Now, we have with circular acceleration, which is defined by the following relation when get here the conservation of angular momentum. L dot, as we said, it's equal to 0. L dot is defined by Rm, the acceleration in phi direction here. Then it will get here R phi dot dot plus 2 times R dot phi dot will be equal to 0, as R and M are not equal to 0. Then it means here the circular acceleration vanishes here. There is no applied force in phi direction, and therefore also no moment around the center E. Now coming to the what we call the work and energy. Okay. Then it means here the work particle with constant applied force. Then we have here this particle. We apply here a constant force, same direction for the force and the displacement. The displacement represented here by ds. Okay, this motion, yeah, um, is um, applied without friction here. Okay, then it means there is only the contact force N here. There is no friction force R. Work along the path element ds here. The work is defined by dv dw, which is equal always to the force multiplied by the displacement. This is the definition of the work. Okay, the work is always the force multiplied by the displacement. Integration with here the work at position, initial position at time t equal to 0. We assume that s is equal to 0. And in this case, if we integrate, okay, we will get w, which is f multiplied by the displacement, or the position here s. Now we take the particle with the constant applied force, okay, different direction for the force and displacement. That is means here we take the tangential one, ft, and the normal one. Okay. Now the force F can be projected here in tangential direction and in normal direction. There is only the displacement, let's say here, along tangential direction ds. The normal force does not contribute since ds is equal to 0. Okay, here there is no motion in vertical or in normal direction. Yeah, this force here will not contribute to make work. If there is no displacement, there is no work. Yeah. Now the work along the S here, as there is motion in horizontal or tangential direction, yeah, and there is force here along this direction, then it means we have here dv is only ft, the tangential one force, which is f cosine phi alpha multiplied by ds. The integration with f, which is constant, we assume that w at s equal to 0 is equal to 0. Okay, then we have here w, which is the work. It's only f cosine alpha multiplied by the covered distance s. Then the abbreviation here, writing of the scalar product. Yeah, this is here represented by this small circle. We call it dot product of two vectors. Okay, then we have A scalar product B. This is always defined by A multiplied by B, the scalar of the vector A, or the magnitude of the vector A, the magnitude of the vector B, cosine alpha. This is the definition of this scalar product, or let's say scalar product of two vectors. It's different from the cross product, the vectorial product. Yeah, it's not the same principle. Then it means here what we have here, f cosine alpha s. Okay, here we can represent it. Yeah, f, this is s vector, then will be here f multiplied by s cosine alpha. This is the simplification, yeah, of method of notation or the abbreviation. Now, if the applet force is not constant, then we have to make, of course, yeah, the integral. Then we have dv here, f it's not constant, okay? In this case, we integrate from S0 to S1, yeah, of ft scalar product or dot product ds, and this is will be ft in tangential direction with um, respect to the time multiplied by ds. Now we take the general case, okay? Not only the motion along the horizontal direction or the tangential direction. We take now this path curve here. What we have here, the particle along path curve with the variable magnitude and direction of the force. That is means here, now, if we take the normal and tangential force, yeah, of this vector force F here, making an angle alpha with the tangential direction. We take the coordinate system x, y, and z. Then it means here there is the vector position r, which depends on time. And here now during the motion, that is mean the change of the distance here, the r, or change of the position vector, the r here. Then we have at time t and time t plus dt. Of course, Fn and Fr will change at this position here. Then the time change of the position vector here, R at time t plus dt, is only equal to R vector position at time t here, R plus dr. Okay, this is the vector here. It's, let's say, the summation of two vectors, R and dr. Now, if we take here the R, the magnitude, it's only the S. Yeah. Now the angle between the R and the force here, it's alpha. Then we have here Ft, the tangential force. It's only here Ft, the projection of this force F here, cosine alpha at time t. The work now, dV, it's only Ft, the time t, at time t here, the tangential force multiplied by ds, as Fn here, okay, now make no work. The change of the distance or the vector distance here is along the radial one or tangential direction, okay? There is no change in this direction here. Then in the, or it's neglected, let's say. Then we have here Ft cosine alpha t ds, as we replace Ft by its expression here. ds is given as the magnitude of the vector position dr. Then we have here, by definition, f vector dot scalar dot product drt. Okay. Now we have to integrate as the force Ft, it's time dependent. Then we integrate here from S0 to S1, or if we represent it by the dot product, then we integrate from R0 to R1, and here this expression F cosine phi ds is only here F cross dot dr. Now we take this particular case, the first one, which is called here guided motion. Okay, you see also here the let's say the first part of the not first part, the first the birth the part 3 at the beginning. We have seen this example here. Now if we take here this sliding mass or particle m, okay, we give it by let's say sliding with ds. We have the contact force here between the ground and the particle m. This is the contact force is n. Now here, as we said, always the contact force is perpendicular to the motion here, as it's perpendicular to the ground here. Then there is no, n make no work with the displacement in the direction of the motion. Yeah. Always the work will be the force in the same direction, yeah, as the motion. This is the definition of the work. Okay. Then we have here dw, which is the change of the work, is equal to 0. Now we take the second case, the motion with resistance force. Okay. Then we have here the contact force N, which make no work, and there is the resistance. That is means here there is friction, let's say. If there is friction, that is defined by R, okay? And R, it's only mu, which is friction coefficient here, mu, multiplied by the contact force N. Now we have the motion in this direction, and we have the force R, the resistance force, in the same direction, opposite, let's say, opposite direction to the motion, okay? Then here we can say the work of the resistance force for the displacement ds in the direction of the motion is always negative, okay? As I said here, with the work by definition, okay, it's the force multiplied by the position or the displacement, yeah, but in the same direction or opposite direction, yeah. In this case, if they are in the same direction, in this case will be positive. If the force is opposite to the direction of the motion, in this case will be negative. Now coming using this, okay, we can come now to what we call the kinetic energy or the work principle. In this case, the acting force, yeah, acting on any particle in motion will accelerate or decelerate it. Yeah, accelerate, that is means is in the same direction. Decelerate, they are opposite direction, as we have seen in the previous. In this case here, this example here, it's opposite to it. That it means is decelerated. That's trying to stop it. Now, the work of the tangential force for the displacement ds Here, W is defined always by the integral, or we make R vector uh, position, yeah, F dot, yeah, R, dr. Here in scalar, Ft s ds, the acceleration following the Newton second law, Ft is only m multiplied by s dot dot, which is the acceleration here. Okay, if we are in place now, we get here m s dot dot ds. With s dot dot, the acceleration is only the time derivative of the velocity. Yeah. Then here ds is only v dt. Okay. As v it's only ds divided by dt. Yeah. Then here we are on place. What we get here, the integration of the right hand side, ft. If we see here now, if we integrate mv dv, m is constant, we get bit out of the integral, then we get v dv is the same variable, okay, the velocity here in our case, then it means it's the half of m, the actual velocity v1 square minus the initial velocity square. This is here we call it the principle of the work. That it means the integral of the applied force, okay, or the work here from the initial position to the actual position, it's only the half of the mass multiplied by the square of the difference of the velocity from the actual to initial one. Now we know by principle, yeah, the kinetic energy is always defined by this relation, the half of the mass multiplied by v square. Yeah, this is the kinetic energy. Then we can say the principle of the work, it's the difference of the actual kinetic energy minus, yeah, the initial kinetic energy. Now we can say that the change in kinetic energy of a particle is the net work done on the particle. Yeah. Now we take this example, which is the brick on inclined plane. Yeah, what we have seen before. We have now this particle or brick, yeah, with a mass m. This is the initial state at time t equal to t0. We assume the particle is at rest. Then we have the velocity v0, which is equal to 0. The cover distance to the actual state at time t equal to t1, it's L. Okay, the whole system is under gravitational field. Now, if we look to this inclined plane, which described by the angle alpha, okay, the high here, okay, delta H, which is L sine alpha, okay. Now we take the free body diagram for the brick. As for the work, we need the forces, okay, and then we look if those forces make motion or let's say displacement along this motion, yeah, there will be the work. If not, yeah, In this case, there will be no work. Then we assume there is frictionless motion. That is means there is no resistance. Yeah, there is only the contact force N, and there is no force along the motion here. Let's say there is no R. Yeah. Now, if we take mg, the weight, mg decompose it into two parts, one in the perpendicular one to the motion, and the second one along the direction of the motion, which is mg sine alpha. Now, if we look here, only the force acting in the direction of the motion are considered. Why? Because there is here, yeah, if we take now the direction of L, okay, of the direction of L, there is the force here, which is mg sine alpha, okay. Now, if we take delta H, yeah, here, as there is displacement, we can take, okay, mg in this case, yeah. Now, what we have here, only the force acting in the direction of the motion are considered. What we have ft, which is the tangential one, or the direction, the tangential one, or in the same direction as the motion here. There is this force here, mg sine alpha. Okay. Now, if alpha is constant, g also, m is constant. That is mean ft will be constant. Now, if we use the work of the principle of work, yeah, we integrate from the initial state, which is at t0, it's 0, okay? And we have here the position, the actual position, which is in our case here, L. Then we integrate, yeah, this is the work W, okay, will be equal the change of the kinetic energy here, which is defined by the half of m velocity at time t1 minus here velocity square at time t0. Now, if we integrate this one, we have ft, okay, given by this expression here. Then we have mg sine alpha. These are all constant. That it means we have to integrate from 0 to L ds, okay? Then will be mg sine alpha s, okay, s from L to or from 0 to L, then will be mg L sine alpha, and this is will be equal to the half of the mass, or the difference between the kinetic energy. The speed v1, we have seen it in the part 1, it's only the square root of 2 times gl sine alpha, okay? And this is will be only 2 times g delta h. Now we take the case where there is a resistance, or let's say there is friction. In this case, there is also here, yeah, the force R, or resistance force, yeah, or friction force R, which is the friction coefficient mu multiplied by this contact force N. Okay. In this case, Ft will be defined here with here mg sine alpha as the previous one. Yeah, we added, yeah, here mu multiplied by N, which is here this force here R. Yeah, and if we make the equilibrium now along this direction, yeah, the sum of the forces In our case, as there is no motion in this direction, yeah, the particle is always in contact with the ground, yeah, then here the equilibrium is equal to zero. That is means here n will be equal to mg cosine alpha. Then we can replace n here in the expression of the tangential force by mg cosine alpha. And now what we have to do is the same principle, okay? The principle of the work here. We say mg sine alpha, we integrate from 0 to L, okay? Then here we get L, and here the half of mv1 square. This is the kinetic energy. The velocity in this case, we have seen it also in part one, yeah, v1 will be square root, yeah, of this expression here. As we said here, fast solution, the Newton's second law or the lumbar inertia force, yeah, but no equation of motion with the acceleration, velocity, and as the only distance depend of the velocity v. Now we take the potential energy in gravitational field of Earth, principle of energy. Now we have the final velocity of a particle in gravitational field of Earth are, yeah, different from the path type. If we take the example of free fall from high h, we found the velocity is given by the following relation. For the circular uniform motion, there is 2t here. For motion with a radius r, v is given by the following relation. Frictionless inclined plane with a length L, v is given by the following relation. One gets in general for delta H, yeah, this expression here, what we have seen before. Now, with initial velocity, which is different from zero, one gets here, okay, the kinetic energy at time t1 is only mg delta h, this velocity here, yeah, plus the half or plus the initial kinetic energy, let's say. Here we're on place. Then we get here the potential energy in gravitational field of Earth, respectively potential of the gravitational force. We note it by the following symbol here, capital letter pi. This will be only the mass multiplied by the gravitational acceleration, yeah, multiplied by z. Z will be calculated from zero level. Okay, this is where we see it, yeah, more in details. Now we have the principle of energy. It's given by the following. Yeah, the sum of the potential energy plus the kinetic energy at time t1 will be equal to the potential energy plus the kinetic energy at time t0. Okay, this is the principle of energy, or let's say conservation of energy. Okay. Now, general formulation without assuming special trajectory path. The principle of energy, okay, this is, we have seen it, is the work which is equal to the kinetic energy. Here, the change of the work, the W, is only the dot product of F with the position, and we have here the R. We have seen it also in part 1. We make the projection along X, Y, and Z direction. Yeah, this is, we can do it by dW, the change of the work. Okay, it's the same principle. The force will be decomposed along X, Y, and Z direction. Now, if we take the Z-axis of an arbitrary zero level, Earth surface, for example, opposite to G, Fz will be minus mg. Yeah, Fx and Fy will be equal to 0. Okay, now dW will be only this Fz here, dz, then it means will be minus mg dz. We integrate, then we have here the work, okay, will be only mg z0 minus z1. That this means it's only a matter of to choose the zero, let's say, level. This is, yeah, we will see it more in details how to do this, yeah, in some practical, let's say, problem. Now, substitution in the principal work, we get the following relation here. This is now the potential energy. This is the kinematic energy, but at time t1, okay? And here the same, the potential energy, the kinetic energy at time t0. Now we take the example, we have seen it, yeah, in part 2, yeah, this vertical throw, okay? What we have here, we have z-axis upward from Earth's surface, yeah? We have here for time t0 with velocity, yeah, v0, we give a certain velocity v0 here, reaching, yeah, at time t1, the high, which is here h0. Okay, we have gravitational acceleration g. Okay, we give certain initial velocity v0. Okay, until reaching t1. At t1, certain times the velocity will reach the value 0. Okay, will vanish. Now, if we apply the principle, what we have here, now it acts only the weight, yeah, as, yeah, Fz now in the direction of Z, yeah, will be only minus mg. This is the force what we get here. It's in the same direction as the motion, yeah. The work along dz, dw here will be only minus mg dz. Work between the time or let's say t0 or z equal to 0, yeah, to z1 at the high one, yeah, or the time t1. This is will integrate now as our variable is the high here, z, then we integrate from 0 to the actual h, which is here, the actual one, which is h. Then we have here minus mg multiplied by dz. When we integrate, we get mg z0 at time t0 here. We have z0, which is equal to 0. Then we have here only minus mg z1. mg z1 z1 is only h. Okay, then we have here the work which is equal to minus mg multiplied by h. The potential energy for z equal to 0 and z equal to h. Yeah. Then what we have here, the potential energy by 0, it's only mg multiplied by z0. As z0 is equal to 0, that is mean its potential is equal to 0. Okay. Now we take at time t1, the potential energy is the same expression mg z1. Z1 will be equal to h. Yeah. Here we note it by, I note it here by h0. Yeah. It's the same. It's not important, the notation. The principle is important. The work now. The work is only the difference between the initial potential, yeah, minus P1. This P0 is equal to 0, then we have only minus P1, and P1 is defined by mg multiplied by h. Yeah. Now coming to the principle of energy. The principle of energy, the sum of the potential plus the kinetic energy, yeah, at time t1 will be equal to the sum of the potential and the kinetic energy at time t0. Now coming to the kinetic energy, this term P1 we have it, P0 we have it, we have to define now T1 and T0. T0, as we know, the kinetic energy always the half of the mass multiplied by the velocity square. In our case, at time t0, the velocity is equal to 0. Sorry, to v0. Okay, but at time t1, yeah, the velocity v1 will be equal to 0. Yeah, the mass m reach certain height, yeah, until the velocity will vanish. Then we get here that the kinetic energy at time t1 will be equal to 0. Then it means what we have here, if we replace now this term plus this term, okay, the first one, P1 is mgh, T1 here it's 0, then we have mgh, the second term now, P0 is 0, T0 it's given by this term, then we have this term here. Then we get h will be equal to v0 squared divided by 2g. Okay. Now we take this free fall, okay, the opposite to the previous one. Yeah. The z-axis here upward, that is means now the motion is opposite to z direction. Yeah. For time t equal to 0, the mass will have the velocity equal to 0 released from h distance here. Now it acts only the weight, of course, as the previous one. The difference now here, okay, Fz will be minus mg, yeah, as it's opposite to z direction here. The work along dz, dw, it's minus mg dz, okay. The integration will give the work here between the z which equal to h, 2 and 0 here. And then we get here the work which is equal to mgh. Now we take the potential energy. For z equal to 0 and z equal to h, we have the potential, yeah, for z equal to 0 or time t equal T0, we have mg multiplied by Z0. In this case, Z0 will be equal to H. Yeah, it's completely opposite to the previous case. Yeah, P1 will be equal to 0. In this case, the same principle. Okay, the principle of energy, potential plus kinetic at time T1 equals to the potential plus kinetic at time T0. Now we have the kinetic energy here at time T0 as I said, released um, from rest. V0 will be equal to 0 and V1 is unknown. Okay, but certain times when the mass reaches the ground, we'll reach it with certain velocity V1. Okay, then we make the equality. We're replacing this expression here, yeah, with uh, the value or the expression of P0, P1, T0, and T1. In this case, we get the velocity V1, which is square root of 2 times GH. And as you see it, yeah, let's say is here the same as the previous one. Yeah, the difference here in the previous one, we know the velocity V0, yeah, and the second one with the free wall. In this case, yeah, we have to determine the velocity, yeah, let's say reaching the mass reaching the ground. Okay, this is we can define by the following, and it's the same expression as we have done it, yeah, in the part two. Now we take this example, yeah, system of two masses in gravitational field. Okay, we have the mass m1, and here we have the mass m2. Yeah, the principle of such application of um, the conservation of energy. Yeah, in this case, we have always, yeah, to try to find what we call the zero level. Means that here we try always, yeah, we will see, as I said it, we will see it in example, particularly, yeah, when we use rigid body, yeah, always to try to find it's free, yeah, it's free to use the zero level everywhere, yeah, but the best idea is to use the zero level where we have all information, yeah, in the general case where we have fixed um, point, let's say, yeah, it's not to choose. For example, in this example here, we know the initial state, okay? As we know the initial state, we can take the zero level somewhere here at this initial state, yeah. It will be complicated. It's not wrong, but it will be complicated for the calculation. If you use, for example, the zero level somewhere here, yeah, it's moving. That it means the zero level will move with, yeah. The best way is to use the zero level, yeah, where the all information, yeah, are given, yeah. Or to use the zero level somewhere here, where this point here is fixed, okay, will not change. If the mass moves, yeah, this point here, the pulley will not change. In this case, you can choose here the zero level, okay. You will find always the same results, yeah. Now, we take here the work of the force of gravity depends here only on the respective height difference. Yeah. That it means now if the mass M1, yeah, move to this position, yeah, there will be the difference, yeah, of the height between the actual position and the initial position. We note it by delta H1. Okay. The same for the mass M2. This initial position, this is the actual position, and now the the change of the distance here, yeah, between the initial and the actual one. This is we noted by delta H2. In the principle of energy, one have only the difference of the potential energy. Okay, that it means we have P1 plus T1 equal to P0 plus T0, or we can write P1 minus P0, which is equal to T0 minus T1. Yeah, it's matter of notation as you can see it here. Yeah, we have the principle of energy P1 plus T1 equal to P0 plus T0, or we can write P1 minus P0 equal to T0 minus T1. Okay. Now each mass can be assigned to its own zero level. As I said, the choice of this zero level is very important. Yeah. Now, ability to simplify the solution of a complex task. Now, work here of the friction force. Now, friction force act always against the motion. That is means there is always here, let's say, minus, yeah, with the force here, minus mg dz, plus here, as the force here, the gravitational is always opposite to the direction of the motion, yeah, and also here the friction force are always also opposite to the direction of the motion, and we note it here by minus. The work integral of the friction force, yeah, we note it by W R, okay, which here it's minus R S1 minus S0. Yeah. For example, we have seen it for friction force in inclined plane. Now, you have to make attention that if the friction force is not constant, this should be integrated. Yeah, that is means R. If it's not constant, depending on the position, yeah, we have to integrate it as it's the variable, integration variable, it's as we have to integrate it. Now the work of the friction force is distance dependent. Now frictional force is not conservative. Now when we take this from conservation of energy, one get here mg z0 minus z1, yeah, as p1 it's mg z1 with a minus, and P0 is mg z0 with a minus. Okay, but in this case here, as there is friction, we have to add the work due to the friction force. Okay, here plus WR, and WR is given, yeah, by this expression here, which is equal now to the let's say the difference between, yeah, the kinetic energy at time t1 and time t0. Okay, Now we have here, if we replace, we get here P1 plus T1, which is equal to P0 plus T0, okay? But here we add the third term, which is here the work, yeah, due to the friction or due to the friction force. Now, WR is always negative. Always negative. Why? Because it's always against the motion. Yeah. Now, the sum of the potential and kinetic energy decreases with the motion. Yeah. In this case, friction force are dissipative. Now, in general, we have this case that here the conservation energy with friction forces, yeah, opposite to that what we have seen, or let's say different from that what we have seen previously. In previous case, this term, yeah, doesn't exist or it's vanish, yeah. But if there is friction, yeah, we have to add, yeah, this term here. Either you make P1 minus P0, yeah, equal to T0 minus T1, but you have to add this term here plus WR, which is the work, yeah, due to the friction force. This is very important, yeah, keep it in mind. Now we take the brake on inclined plane for t equal to 0, yeah, here, moving along this direction here, okay, downward. For t equal to 0, we have the high, which is from the ground, h0, yeah, that we say that start the brake from state of rest, which is v. In this case, the velocity is equal to 0, okay, at time t0, v is equal to 0. For time t1, reach the brake, the high h1, okay. The question is, what is the velocity v1? Yeah. Now, if we apply the principle of energy, in this case, there is no friction, okay? Yeah, for this example, that we neglect this term here, yeah? Then we have zero level is set by the wedge tip. That is means we put here, yeah, the zero level somewhere here where it's fixed, okay? As I said, the zero level is always you have to choose it. Otherwise, yeah, with zero level means there is no potential energy. Okay, this is what it means is zero level. There is no high, there is no distance. Okay, when you make the force multiplied by the high, in this case for the zero level, it's zero. Yeah, for this we have to choose it. The potential now, P0, it's mg multiplied by h0, okay, at time t0. If we choose here the zero level, P1 will be also mg multiplied by h1, okay. Mg, it's in this direction, yeah, and the high also in the same direction. It's always, yeah. Now the kinetic energy, T0 is defined by, as always, by the following relation. In our case, V at time t0 it's equal to 0. Okay, then the kinetic energy at time t0 it's equal to 0, and we have at time t1 is the half of the mass multiplied by the velocity 1, what we are looking for. Yeah. Now we apply the conservation of energy. Yeah. The potential energy at P1 plus the kinetic energy T1, yeah, will be equal to the potential energy P0 plus T0, which is equal to 0. Okay. Then we get here the velocity from this expression here. V1 is square root of 2 times GL sine alpha. Okay. This value, we have seen it already. Yeah? Now, if we take the motion with friction, yeah, friction force here, if we take the friction force R, we have the force N here, okay. R is against the motion, and the contact force, we can make it in equilibrium with the weight mg, okay. Then we have only to make N, yeah, or you make either N along um, G direction, the vertical direction, then you project it with respect to the angle alpha, or you make mg, yeah, projected along the N direction, yeah. Then in this case, we have here R, it's only mu multiplied by N, okay, and N it's mg cosine alpha. The contact force N, it's mg cosine alpha. In this case, it doesn't depend on S. Yeah. Okay. We have not to integrate R. We can keep it out of the integral. Yeah. Then we have WR in this case. It's minus mu mg cosine alpha multiplied by L. Okay. L, it's the cover distance. Yeah. From 0 time T0 to T1. Okay. Now the principle of the work, yeah, is the same as this one, but we have to add here the work due to the friction force. And this is the friction force here, the work due to the friction force. Okay, now we get here the velocity V1, okay, by the following expression. Now, if we take this example here, the potential energy of spring, yeah. Now we take the spring is in undeformed state with elongation x, that is means here there is the elongation x, yeah. Initial state, it's L0, okay. The spring has the, the elongation or the length L0, okay. If we make the body diagram, okay, we cut, there is the spring force, yeah, which is always spring's coefficient C multiplied by, yeah, the elongation x, okay. The motion is along x direction. Now, the work of the displacement dx, okay, dw, it's only the force multiplied by the elongation, the change in the elongation dx, as here the force on the mass, okay, it's the spring force, yeah. Then we have here minus cx multiplied by dx. The work from x uh, equal to x0 to x1, okay. Now what we have here, we integrate this expression here, yeah, of the change of the work here. Now from x0 to x1, minus Cx dx. C is constant. Yeah, we put it out of the integral. That is means we integrate x dx. Then x dx gives x squared divided by 2. Then it means we have the work here, the half of Cx square minus the half of Cx1 square. Then it means here W depends only on the start and end position of the spring and not on the displacement path. Yeah. Now the force, the spring force is conservative. Potential of the energy can be put here. Pf is the half of Cx square. Okay, this is the kinetic energy and this is the potential energy. Now the work of the spring. W will be here the difference between the initial and the actual state of the potential. Based on the non-stretched spring, the work is here W, which is equal to minus the potential, yeah, of the spring at time t1 or actual time. Now we have this sign negative as F is opposite to X, okay, the direction of the spring motion. Now we take this example system with the spring, okay. Now we take this mass M or the particle connected to the spring, okay. And now this mass moves, yeah, with friction here, R. We have the contact force N between the ground and the mass, okay. We have the projection of the weight here, G, which is mg, yeah, the mass multiplied by the gravitational acceleration here, noted by capital letter G, okay. Then mg has two components, G cosine alpha in vertical direction and G sine alpha in horizontal direction. The friction is against opposite to the motion here. Now, starting point, yeah, at time t equal to 0, we have the high here, h0. The spring elongation is x0. Yeah. Force along the path, what we have the projection of the weight, yeah, and here G sine alpha minus, okay, spring force, yeah, when we make the body diagram here, when we cut here, we have the spring force, which is F opposite, okay, this is minus F, and additionally, we have the friction here between the mass and the ground. We note it by minus R, okay? Now, summation integration and the integration of the work with respect to displacement ds, okay? We have the work here for the tangential force, okay? Then we have mg h0 minus h1. This is the potential energy. The half of Cx0 square minus half of Cx1 square. This is the, let's say, the potential energy, yeah, with respect of the spring. Yeah. As we have said, the work or the potential here is the half of Cx1 square for the spring. Yeah. Here, and additionally, we have the work due to the friction. Now, if we take here W, okay, which is here the difference between the actual and the initial potential, yeah, for the mass M, for the spring, and for the friction here. Then we have the principle of work. Okay, the work also has the difference between the kinetic energy at actual time and the initial time. Yeah, the actual time has the velocity v1 and the initial time has the velocity v0. Okay, we replace everything in the expression. Yeah, the expression that is means we substitute now in the expression of the conservation of energy. Now, case of frictionless, there is no friction in this case. This term here vanish. Okay. Now we take here this example, which is the free fall of elastically suspended table. Okay. Now we take zero level at the top of the table in rest. That is means here we take the table. Okay. This is the zero level. Yeah. As I said, it's free for you. Yeah. To choose where is the zero level. But to be a little bit clever, to use, yeah, where, as I said it, where you have all information. Okay, you can choose it here, yeah, at this position, yeah, the contact between the spring and the ground, let's say, yeah. You can choose it at this position here when you know the velocity v0, or you choose it here, okay, at this what we have, we do it here now, okay. What we know the height of the mass, yeah, at the initial state, T0, okay. The free fall of the table here is at the position H, the height H here. We take the zero level here, okay. Now when the table at the actual time, yeah, we have the spring will be compressed, okay, with let's say X, yeah. What we have here at time t equal to 0, the high h and initial velocity v0 downward. At time t equal to t1, the maximum elongation, yeah, then v will be equal to 0. Okay, then it means it's compressed until, yeah, it will be stable, and in this case, yeah, the velocity v will be equal to 0, where the x, yeah, the compression or of the spring will be at its maximal. Yeah, maximal in the sense of absolute value. Yeah. Now, if we look to the expression of the potential and kinetic energy at time t equal to 0, t0, the kinetic energy, the half of the mass multiplied by the velocity. The velocity is v0. Okay. Now coming to the potential energy. Potential P0 as the zero level, it's here, okay? Then it means now what we have mg multiplied by h. Yeah, this is the distance from the zero level to the, yeah, um, let's say applied uh, force, which is in our case here the weight. Yeah, if you put the zero level here, in this case, the potential P0 will be equal to 0. Okay. If you put the zero level here, yeah, this will be H plus, yeah, the let's say the length of the spring here. Yeah, this is, as I said, it's depend where is the zero level. Now the spring, yeah, it's unstretched in this case. The potential of the spring will be equal to zero. Okay. Now at time t1, yeah, t1 at this position here, let's say, or at this state here, what we have the kinetic energy, which is equal to zero. Okay. Why? As we said, reaching the maximum, yeah, the elongation, let's say, reaching its maximum, yeah, this mass will be at rest. Yeah. Then in this case, we have P1, yeah, the potential energy of the mass M will be minus mg x max. X max, it's only the elongation of the spring. That is means, yeah, it covered certain distance x here. Yeah. Now the potential energy of the spring, as defined before, is the half of C, the coefficient, spring coefficient here, multiplied by x max square. Okay. Now, if we replace here motion without friction, that is means WR will be neglected. In this case, when we apply the conservation of energy, here we have minus gmg x max for the potential P1, okay, plus the potential of the spring, which is equal to P0 mgh plus T0. Okay, if we replace now, we get, yeah, X max here given by the following initial, that is means there is two terms, plus or minus, okay. The negative solution is to be rejected, yeah. Then it means we have to take here mg divided by c plus the square root of this expression here. Then it means here the maximum elongation of the table here, x max, is given by the following relation. Now, if we replace the maximum spring force, yeah, the force applied on the spring, F will be only C multiplied by X max. Okay, this is the definition of the force in the spring. Yeah, we are replace only here X max by its expression given by, yeah, this relation here. I will stop here for today. Yeah. Um, yes.